What is the derivative of a power function? For a power function of the form f of x equals x to the nth power, its derivative, f prime of x, equals n times x to the power of n minus 1. First, notice that the exponent n appears as a coefficient in front of the power function. Then, you subtract 1 from the original exponent. We'll show you where this rule comes from at a later stage. To understand this rule better, let's look at an example where we first use the rule, then check the result using the definition of the derivative. Using the rule, you will find the derivative function for f of x equals x cubed. To differentiate x cubed, the exponent 3 will appear in front of the power function, while you subtract 1 from 3, leaving 2 as the exponent, like this. So, the derivative of x cubed is 3x squared. Now, let's use the definition of the derivative to check the result. You insert the function into the definition, which gives you the quantity x plus delta x cubed minus x cubed in the numerator, and delta x in the denominator. Recall that the quantity x plus delta x cubed equals the quantities x plus delta x times x plus delta x times x plus delta x. When expanding the first term, you multiply 2 of the pairs of parentheses by each other. Here, you can use the square of a sum formula, and you get x squared plus 2 times x times delta x plus delta x squared. Remember to write this inside of parentheses. If you are familiar with binomial expansion, you can also use that to write out x plus delta x cubed directly. Then, you multiply the 2 pairs of parentheses and get x cubed plus x squared times delta x plus 2x squared times delta x plus 2x times delta x squared plus delta x squared times x plus delta x cubed. You still have the minus x cubed in the numerator. Now you group like terms, which leaves you with 3x squared times delta x plus 3x times delta x squared plus delta x cubed in the numerator. You factor out the delta x as a common factor from all the terms in the numerator, which allows you to cancel delta x in the denominator. Now you evaluate the limit of 3x squared plus 3x times delta x plus delta x squared as delta x approaches 0. As delta x approaches 0, the terms containing delta x will approach 0 as well, leaving you with just 3x squared. To summarize, using the definition of the derivative, you found that for the function f of x equals x cubed, the derivative function f prime of x equals 3x squared. Nice! You got the same result as when you used the rule. You probably noticed that using the rule is way faster and much easier. Remember, there was nothing special about the exponent 3 in this example. N can be equal to any number. For instance, if you want to find the derivative of g of x equals x to the 13th power, you can use the rule and get g prime of x equals 13x to the power of 13 minus 1, which equals 13x to the 12th power. But what happens if n equals 0? Then, as the exponent appears in front of the power function, you end up multiplying by 0. You probably noticed that x to the 0th power is 1, so the derivative of 1 is 0. This happens to be the case for all constant terms. The derivative of a constant term is always 0. At a later stage, we will show you why. But what happens if n equals 1? According to the rule, you end up with 1 in front of the power function, and 1 minus 1 in the exponent. Multiplying by 1 changes nothing, so let's just ignore it. 1 minus 1 equals 0, so you're left with x to the 0th power. As mentioned above, this equals 1. Notice that the function you started with, x, is the same as 1 times x. And the derivative of that function equals 1. It turns out that this pattern would also hold for any other constant in front of the x. The derivative of 2x equals 2. The derivative of 5x equals 5, and the derivative of 287x is 287. In general, for a constant, c, the derivative of c times x equals c. At a later stage, we will show you why this is the case. For a power function of the form f of x equals x to the nth power, its derivative is f prime of x equals n times x to the power of n minus 1.